This is a presentation adapted from one given in October. The slide deck was originally prepared by Ben Bross, who is the main editor of VVC. I'm a co-chairman for the development of VVC. It's the next big video coding standard. So VVC is versatile video coding, and we're almost finished with the standardization process of that. So I have a slide deck here that should take about 25 minutes. If anyone has questions or comments, feel free to interject because this is for you, not for me. Moving on, it's a joint project of the I2T VCAG group and the ISO IEC MPEG group, as has been the case for several previous big generations of video coding standards, known as MPEG-2, H.264 or AVC, or HEVC. And now VVC is the next big one, and we're aiming for about 50% lower bit rate than HEVC for the same perceptual video quality. So a big advance in what we call coding efficiency, the ability to code video with as few bits as possible. That, I guess, is the main goal of the project, and has been a pretty compelling proposition for previous video coding standards as well. In terms of what we're focusing on for the project, we're emphasizing high resolution video more than ever before. HD, Ultra HD, 4K, and 8K video, and also high dynamic range video. We're also emphasizing 10-bit video primarily. Previous generations, we mostly worked on 8-bit video and sometimes didn't even have 10-bit video capability, or not until a subsequent version of the standard or something like that. But that's the basic, ordinary applications of video. And the other big goal is what we call versatility, trying to further broaden the range of applications. There are several components to that versatility aspect. One is screen content coding, so efficient coding of rendered screen graphics, any kind of computer-generated content, anything that did not come from a camera. We have special features that are better at that than has been the case in any previous standard designs. We also support adaptive resolution changes. So for example, in video streaming, if your bit rate is fluctuating and your service provider wants to drop you from 4K to HD, or things are going quite well and you can bump up in resolution, you can do that in the new codec without sending an iframe, so without resetting the whole decoding process. You can predictively change resolution. We also support independent coding of subpicture regions, which could be useful for things like mosaicing of multiple participants in a video conference, or combining different video streams with each other after the fact. There's lots of different applications for that. Bitstream extraction and merging, it can be used with that, so you can composite a new video together from pieces of other videos. And we also support layered coding with scalability. That's typically something that we do in second or third version of a standard, but we're doing all that in the first version of VVC, along with multi-view and that sort of thing. So very broad range of applications. But the fundamental goal is coding efficiency here we have a chart of like how many bits it takes to get video up to a given level of quality. Here we're just using PSNR as an example of distortion measure. And if we look over time at the different standards that came out in different generations, the number of bits needed to get a given level of coding efficiency has gone down. We keep with each major generation trying to get a major reduction in bit rate. Often we try to shoot for about 50% for the same quality, and we're trying to do that again with VVC. Now, some people would say, well, you know, now we have enough capability. You know, do we need more efficient video coding? Because after all, if you could send video with MPEG-2, and now with HEVC you can send it with only 25% as many bits because we've gone through two 50% bit rate savings since then. Why do we need to keep pushing on that boundary? Well, the sad fact is that video is still 80% of internet traffic and is actually rising in percentage. So video is really the driving force of what people are sending and storing worldwide. And it actually is a maxim that people use more of something if they're using it more efficiently. So people want more video. They want higher resolution video, higher frame rates, fancier capabilities like multi-view and high dynamic range and all that sort of stuff that want more and more. And so the traffic of video is continuing to rise, and more efficient video coding is almost always worth the extra effort involved in trying to compress it. So our target is about a 50% bit rate reduction again relative to the previous generation of HEVC. In terms of timeline,
hey, Gary, real quick, yes? What do you can you elaborate on multi-view? What exactly do you mean by multi-view?
Oh, for example, stereoscopic video coding or higher dimensional multi-view. You know, there are fancy multi-view displays and technologies where you could like switch between which streams you're looking at depending on your perspective. That kind of stuff.
Got it. Thanks.
Yeah. So we started exploring the possibility of beating HEVC as early as 2015 and had a call for proposals which followed a pretty extensive collaborative exploration phase. We developed something we called the JEM, which developed over time. It started as about 10% better than HEVC, and by the end of 2017 was 34% better than HEVC in compression, although not so practical. And then we launched a call for proposals and went into a real development phase of the standard 2 years ago. And we expect to be done 2 months from now. So July of this year is our target for being completely finished. And we're trying at this point to work out all the final details. In the call for proposals, we got proposals from 32 organizations, and subjectively, we were getting 40% or more bit rate savings from a number of those. We did a formal subjective test for that phase of the project, and we will do that again. That's not something we do very often because it's difficult and time consuming and expensive, but we're pretty confident that we've gotten a lot of coding efficiency benefit, and that was shown even in the call for proposal stage. We started off with sort of a clean slate approach, adopting a flexible partitioning scheme called the quad tree with multi-type tree. And then we sort of incrementally added coding tools on top of that to gradually get to where we are today. In terms of what is in the design, well, there's a fairly long list. Over time, it has gotten harder and harder to get compression benefit, and so we've gotten more and more things that we started putting into the standard to get that. Many of them are only giving us a small % bitrate savings, and so you have to combine quite a few of them together to do a really good job. But maybe I could highlight a few of these a little bit. I'll go into a couple of those in more detail, but the adaptive loop filter is one that provides a significant gain. Affine motion comp is interesting. That can model zooming and that sort of stuff more efficiently than traditional techniques. The triangle partitioning mode is interesting. It can approximate the shape of objects much better than the old block segmentation kind of designs. Bidirectional optical flow is interesting. There's some motion estimation inside the decoding process for that. And so that's pretty innovative. Intra-block copy is good for screen content coding. You can repeat areas of the current picture in a way similar to motion compensation, but operating in the current picture. Decoder side motion vector refinement is another search technique inside the decoder. Again, something that's not typical in video coding designs. Let's see, here's an illustration here on the right of the kind of segmentation that you might get with VVC. And for those of you familiar with other previous specs, you'll see, for example, in this area here, there are some segmentations that could not have been achieved with previous standards. The sort of 1/3 and 2/3 splits and multiple horizontal splits at sort of unusual locations. These are segmentations you would not get in previous schemes. And the geometric partitioning can be even more general than that. So generally, there are a lot of incremental improvements. The basic design, though, is still the classic hybrid video coding model with motion compensated prediction, mostly using blocks, and then transform of the residual and a quantization, which is often sort of scalar quantization, although we've gotten into a bit fancier territory with this dependent quantization scheme. Here's a diagram over time, over 6 generations of our video test model. We see what has happened to coding efficiency in the green curve. We started out about 10% better than HEVC, and now we're on VTM9, and we're about 40% better in PSNR. In subjective quality, we're even better than that. But so you can see that over time, the coding efficiency has gotten better and better, although it has started to plateau, and now being done with the project, we're at about 40% in PSNR for HD and Ultra HD, and subjectively, we're probably better than that, in the neighborhood of 50% bit rate savings. Now, the other two curves here are interesting. The bottom one is decoder runtime. So this is how long it takes the decoder to decode a given set of video frames. And so currently our video test model is maybe 60% slower than HEVC decoding. So there is some significant increase in complexity for decoding the video, but it's pretty manageable in generation after generation. 2 to 1 or even 3 to 1 has been considered acceptable, so this should not be too hard to implement. I think generally anybody would agree that we've got a very implementable video coder. On the encoder side, in our test model, the encoder has gone up around, now we're at like 9 times the encoder runtime. So it takes a lot of processing power to do an encode. Although there's a lot of trade-off that you can do, there's a lot of optimization you can do. The encoder is entirely outside of the scope of the spec, so it's not. This number is not necessarily indicative of what you'll encounter in the real world, but I think it's well understood that number one, it is more complex to make a VVC encoder than an HEVC encoder. Number two, it's also practical. It's within the bounds of being reasonable. So people ought to be able to do it without too much trouble. If we look at the PSNR gain, I think if we look historically, HEVC versus AVC was about 36% gain in PSNR. It was more than that subjectively, and we think we've done that again. So here again, I would like to emphasize, although this curve is showing a 38% bitrate savings, subjectively, I think we're doing better than that, and that's important for people to understand. So basically, in
Gary,
terms
there's
of
a question.
yes?
There's a question in the chat, which I can read out to you. What kind of content are these bitrate savings being measured with? I think you made reference to a specific test set of test content.
We have what we call our common test conditions, and that includes what we call classes of content, and we have different classes for HD and 4K and lower resolution. So we also have what we call text and graphics with motion class. What is shown here, what we usually plot is either the average of the HD and Ultra HD classes, or the average of all the classes, not including screen content coding. Screen content coding, we're doing even better, but it can really skew the averages if you include that. It's not dramatically different, the amount of compression gain we're getting in different classes, but we do tend to do better on high resolution material and on screen content material in particular. And high resolution is our main focus. Okay?
Thank you.
So generally, the coding efficiency part of the design is very mature and well debugged and quite well designed. It's been studied by hundreds of people and well understood. The versatility aspects are the part that we're in some ways still working on. But we're getting very close to finished with everything, and like I said, trying to be done completely in 2 months. Just to emphasize a couple of important areas. One is screen content coding. So if we have anything that was not generated by a camera, that was rendered, especially sort of hard-edged graphics, that's what we call screen content coding. And we have several new features in there. HEVC had some screen content coding extensions, but those were not included in the main profile. And so they did not end up getting implemented by most implementations. For VVC, screen content will be in version 1. It will be in the main profile of the standard. We're not planning to make any profiles that don't support those features. And so it will be quite a strong package for screen content coding. Another aspect that I talked about before was this reference picture resampling that lets you adaptively change picture resolution from picture to picture. And if we have that feature, it also becomes very natural to support spatial scalability. So we have kind of a unified design for spatial scalability and also adaptive resolution changes. Then to focus on this independent subpictures concept, we have the ability to code regions of a picture as independently decodable pieces. And then you could rearrange those pieces or decode them separately in a decoder. You could just decode, say, the region that you're interested in if it's coded as a separate subpicture, or you could mix a subpicture with another subpicture from somewhere else and create a new video composite that way. You could extract a region and send that as a separate bit stream. So there's some new flexibility there in terms of the subpictures. The versatility aspects are almost done. That's what we've been working on mostly for the last few months, and tidying up all the high-level syntax, getting all those details right is what we're focused on right now. In summary, we have these two emphasis areas of coding efficiency and versatility, especially focused on HD and Ultra HD. We think it's practical to implement, and we also have built in some significant extra versatility features that we think are very interesting for a lot of applications, and people will find new applications and new ways to use those things. We're almost done with the final standard. We just had a meeting a couple of weeks ago, a virtual meeting, which is a new experience for us, and we will have one more coming up at the end of June, and then that's it. We also have some ad hoc group meetings that'll be happening in a couple of weeks, but we're almost done. We can taste the end of the of the project at this point, and so it will be a new major generation of video coding standard from ISO, IEC, and ITU, and available for implementation, by the fall of this year. And we should expect to start seeing it showing up in products, depending on the product area, soon after that. Maybe I'll just stop there and take questions for further details about any aspects of deployment or what happens after the standard is finished.
That sounds fantastic. Okay. Thanks, Gary. You can either unmute yourself and ask a question, or if you want to type it out, and I'm happy to read it on your behalf. Either way works.
Well, I love talking. Hi, this is Andy.
Hi, Andy.
So, Gary, adaptive resolution change. Oh boy, let's talk about people. There's no more Kilroy involved. Now, Nicholas, yeah. Yuri, Iraj, and I have been active in the Dash Industry Forum, and I've always been an advocate for deeper use of horizontal and vertical subsampling. What we've got now with MPEG blessing, ISO MPEG blessing, is adaptation set switching of that's fragment aware, so we can support low latency, and so people can have parimutuel betting on the sporting events and all kinds of good things like that. But that requires access points, and now you're switching the resolution without the access points. So considering that Dr. Stockhammer believes in his heart and soul that everything in MPEG Dash should always be codec independent, which person is going to get stuck, I mean blessed, with the opportunity to ensure that there's liaison between low latency standards? I mean, FFmpeg now supports low latency mode with fragment access point requirements. Who's going to carry the torch and possibly light a fire under Qualcomm?
Yeah, well, indeed, this is more flexible than, if that was a feature that Kilroy touted a lot for Windows Media Video 9. We actually had something like that long ago in an optional annex of H.263. Yeah, now it's here in the video layer. How much it gets used in the system layer, as you said, is an important thing. I think actually that some of the work in Dash and things like that may have already been done to support these things. The systems group folks in MPEG are quite enthusiastic about this. And they have been working on it. Some of the people there in particular include like Yakui Wang and Miska Hanuksala, but it is probably a bit more difficult to use those features in a system environment than just switching of independently coded segments. So it will take a bit of work to take advantage of that in a system. So it's up to the industry to see that stuff actually getting used. But it's with VVC, it's going to be there in the video layer. It's available. And I know that the systems folks have been thinking about it, but what actually gets deployed, that's a tough predictor.
Can I tell Rufel, R&D at Unified Streaming, he should have a friendly email with you? Because the folks you mentioned on MPEG systems are not members of the Dash Industry Forum, or if they are, they never contribute. And it really is, I'm waiting for John Simmons or Yuri or Nikolai or Iraj to step on me or cheer me forward. But there's a human connection here. Like I said, the DVB just paid for an upgrade to FFmpeg to support low latency mode. If that becomes obsolete this fall, there's going to need to be conversations, and you haven't mentioned a single person's name yet who's in a position to politely show respect to the company that makes all the cell phone chips.
Yeah, well, the people like Qualcomm and MediaTek and Broadcom, implementers of high volume implementers have been involved in the standardization process and seem comfortable with what we have produced. But maybe I'm not the best person to ask about that aspect of how it's going to get deployed out. You mentioned Iraj's name. I was talking with Iraj earlier today, and it's a good conversation to open up.
Hey, Garen.
Hi, John.
Hey, so has any discussion taken place about a CMAF binding for VVC? Because that's the path to this discussion about low latency and streaming and Dash and so forth.
I haven't seen anything. There's some new CMAF profiles for HEVC that are being worked on now, but I don't think I've seen any new drafts for the CMAF, which for the rest of you, that means Common Media Application Format. It's kind of a contained profiling of several technologies together to make it more focused on a cross-platform implementation space.
It's principally, in this context, this is all the low latency streaming and MSE support are part of the requirements for the streaming,
Mhm.
and adaptive delivery and fitting into MSE. That layer is what CMAF is capturing. And so the path to getting the issues resolved that Andy's talking about, I think would be, the first step would be some submission to CMAF on a binding for VVC.
Mhm.
A couple of possibly somewhat random questions. So I have another kind of profile question. So with both AVC and HEVC, there's the concept of different profiles, main, high, etc. Is that also the case with VVC? And maybe you've talked about it and I missed it, so I apologize.
No, I didn't talk about it. At this point in the draft, there are, I think, 4 profiles. So there's the main profile, and there's 444 profile. Both of those are 10-bit, and they're they're straightforwardly related to each other. And then there's this 2 still picture profiles. I think there's a 420 still picture profile and a 444 still picture profile. And that's it in the current draft. Now, we had a proposal at our most recent meeting that came in asking for a profile without support for scalability and sub pictures. We deferred that to the next meeting to decide whether we will make a profile split on that basis or not. So that will be decided at the end of June. And it's kind of a tough decision. That's still an open question.
Thanks. And then the other question I had was, generally speaking, we see file-based use cases coming out first, and then followed by live. And oftentimes there tend to be trade-offs in terms of what you can do with a live stream in terms of analysis from a transcoding, from a compression standpoint.
Yeah.
I assume the same holds true for VVC, but has there been any specific thinking about live?
I think the basic issue is always the same, that we have an increase in complexity. If you want to get better compression performance, you need to increase the amount of processing power you devote to the encoding process. So doing that in real time is tough. It's always easier to do it if it's an offline encode process. So the live applications tend to lag behind. But I think that there will be some live encoding stuff that's reasonably good coming out as robust products within 2 years or something like that. I'm sure there will be some products right away saying we're doing it now. How well it's being done in the first generation of products is, there might be some bugs in the first generation of products. Traditionally, hardware lags behind the standardization by about 2 years. But there should be low power and you know, robust hardware coming out in a couple of years after the standard is finished. A lot of that's going to depend on demand. You know, people have to, the chip makers have to see the demand there from customers to really burn things into silicon in large volume. And there's an increasing number of codecs being deployed in products now. People are having to make tough decisions about what to prioritize because we increasingly live in a multi-codec world, and different companies have to decide, you know, which direction they think things are going to go and what fits their business strategy the best. But you know, today we have everybody using AVC. Some people still using MPEG-2. Some people using HEVC. There's actually quite a lot of market penetration of HEVC, especially for high resolution video. And then AV1 is now emerging, and there's a lot of interest in that from the implementation community lately. So now we also have VVC coming in. VVC definitely offers a compression benefit, but you know, it's coming along at a time when there's other stuff happening in the industry. And there's also another one called EVC, which was developed in MPEG, but by a smaller number of people than VVC, and so that will be coming out in some products as well. So there's quite a lot for the application world to deal with in terms of what to implement looking forward.
Great, thank you. Does anybody else have any questions? Got a few people who are connected. Again, you can either unmute yourself and ask or just type it into the chat. Gary, I did post a link to the JVET site and with the links to the SDR, HDR, and 360-degree common test conditions, because I know there was a question about that. Great. Well, if there aren't any other questions, Gary, thank you so much for the presentation. Oh, I have one more.
Okay. Chip makers. You mentioned Qualcomm, MediaTek. Who is the third one who's already engaged and aware?
Broadcom is very, very involved. They're different from Qualcomm and MediaTek, where Qualcomm and MediaTek focus mostly on like battery powered devices. Broadcom is more of a set-top box or you know, powered device maker. So it's somewhat different market for them, but they're also a very high volume implementer. And you know, everybody is there. You know, everybody is paying attention. You know, of course there'll be graphics vendors and so forth. You know, everybody is paying attention to this codec, but those are three that are chip focused high volume implementers.
Great, thank you. Thanks, Gary. Thanks so much for the presentation. Really interesting to get it straight from the source.